What exactly is period?
Period is the time to go around once.
So it's seconds per rotation.
It's seconds per rotation. In general, it's the time to repeat a pattern. So it's and we call a repeating pattern a cycle. So it's the number of seconds to complete one cycle. But in the case of a circle, yes, it's seconds per rotation.
Seconds per actually.
Seconds per rotation.
If I just see my lab.
Yeah. I'm not too picky about that.
Like I'm not gonna think it's like not change anything, but so seconds per rotation.
Mm-hmm.
So in a case like this, where it says that like it's 33 rotations per minute, so should it be 60 divided by 33?
So it's 33 seconds per minute, or rotations per minute, right? And then you got, so you want to get rid of the minutes. You got 1 minute on top divided by 60 seconds. So it's divided by 60. Yeah.
Okay.
That's it. You got it.
So it's 33 on top, 60 on the bottom.
Yeah.
Okay.
Mm-hmm.
Okay.
Okay, let's go over 3 and 4 here.
Wait, but wouldn't that turn into rotations per second, not seconds per rotation?
Yeah, that gives you frequency. So rotations per second is the inverse, right? To get period, you got to take 1 and divide it by that. So what I just said is the following. What you just calculated is what's called the frequency in rotations per second, right? Whatever the number is.
Right.
Period is 1 over f.
So that I have to divide it again to get the.
Yeah, you have to take 1 and divide it by whatever that number is.
Can I change it?
Yeah. Why don't you do it after?
All right.
Like I'll allow everyone to do that if they need to.
Oh.
Because I'm not taking it until the end of class. So I'll give you some time at the end of class. I got go over 3 and 4 to start the new unit. So okay. So
Thank you.
You're welcome.
Wait. So.
Okay, 3 and 4, and then we're moving on to the new unit. So question 4 is the end of the circular motion unit. You'll be tested up to including this section. Okay, so let's go over 3 on page 253. You have a satellite. It's about 5.6 million meters above the surface of Jupiter. Calculate the speed of the satellite. So you know how to derive this. I'm doing it again for you one more time. You need to know how to derive it. I can't give you the formula that relates the speed of a satellite going around the planet. That you need to know how to derive. So you start off with centrifugal force is equal to mass times acceleration. Pay attention to the right side. Usually it's v squared over r. Sometimes if they mention period of a satellite, you have to use the other equation. The other equation is, I'll write it down for you. So the alternative is, if they mention period, 4 pi squared r over t squared. Okay? Okay, so back to this. What's keeping any satellite or moon in orbit? It's gravity. So that's what goes on the left, where small m is the mass of the satellite or moon, and m in this case is the mass of Jupiter. Okay, you don't need the mass of the satellite. It will cancel out. You just need the mass of Jupiter. Okay, one of the radii cancels out. So you get G, M, mass of Jupiter, over R is equal to V squared. I'm going to take the square root. That's your final equation. So, one thing before beginning, remember that they give you the satellite's distance above the surface. So R, this R here, is equal to the radius of Jupiter, which is given, plus that height. So I'll just write in the values for you so it's clear. Radius of Jupiter is given 7.18, about 72 million, 7.18 times 10 to the 7, plus the height, 5.6 million meters. Wow. That's your R. I'm going to include that. That's going to go in here. Okay. Mass of Jupiter is included. Let's see how big it is, right? The Earth, if you go back to the Earth and go back to the mass of the Earth, it's a lot smaller, right? It's 10 to the 24. This is 10 to the 27. So Jupiter is massive. Over, we can put it in brackets, this here. $72 million meters. It's also pretty wide, right? So the Earth is is in the millions of meters. Jupiter is in the tens of millions of meters. Okay, so that works out to be 4.1 times 10 to the 4, about 41,000 meters per second. Has to be moving at to stay in orbit. That's the speed it needs to maintain that orbit. If it slows down, it drops. This distance here will drop down. It speeds up, then it moves up higher in altitude. Okay, read over 4 to yourself. I'm not going to derive the equation this time. I'll just give it to you. This is actually the mass of the sun. So make sure you're clear on this. Big M now is whatever is in the center, and that's the sun in this case. If use the mass of the sun. Should be 30. And this is just an average. The radius, the orbital radius. These two values are given in your formula sheet at the back of the formula sheet. Both the mass of the sun and the orbital radius. This is called orbital radius. And that's about 30,000 meters per second. Okay. New unit. Y'all have a little time at the end to work on the practice test. Electrostatics. So electro, I know what I'm doing different. I got to write like this. This is helpful. That's why I wasn't writing neatly. Electrostatics. Electro means, electro is pertaining to electricity, obviously. Statics referring to stationary. Okay, so this is the physics of static charges, charges that are stationary. So just a couple of reminders. You already know how to deal with charges. Charge is probably the most common charge that you're used to dealing with is a proton and an electron. So proton, let's say you have a proton. This is a proton. You have another proton. Okay, you already know this. Opposite charges, or excuse me, like charges repel. Okay, like charges repel. Like charges repel. So that could be two protons, it could be two electrons. That's your number one rule, right? Same thing applies to this. They repel. Second rule, opposites attract. Second rule, opposites attract. Okay. So these are all electric forces. Electric forces. Like instead of Fg, we're going to start using Fe. Electric force. Electric force. And this is, you can call it F, this is object 1, object 2. This is Fe1, this is Fe2. And the forces are opposite and equal. In this case, the forces so Fe1, we usually just deal with magnitude, absolute value, but you do need to know the direction. You need to state the direction at the end. So you need to be aware that, yeah, they're equal in magnitude, but they're opposite in direction. Okay, obviously a couple of other things. This is not rules, but this comes into what we're going to discuss next. So this is, I'll title it Coulomb's Law. It's a fellow who discovered this law. Just keep in mind, we're going to use the following symbols. So Q, either big Q or small q. Either one. It's charge. The amount of charge, actually. I should write amount of charge. Amount of charge. And the unit we use is coulombs. Big C. I'll put it in a different color. Coulombs. So just to give you an idea, an electron, E stands for charge. This stands for what's called elementary charge. And it's the charge on an electron or proton, absolute value. It's equal to, I'm just giving you the absolute value, 1.6 times 10 to the negative 19 coulombs. So Coulomb is Coulomb contains quite a few electrons. Electron has a very, very small amount of coulombs of charge. Okay. So just to give you an idea of the size. Again, this is the absolute value. For a proton, it's positive. For electron, it's negative. This is located in your, I think it's E. Most data tables call it or label it E. Why don't you check, just so you know where, because we're going to use it a lot. Make sure it's there. It should be there in the back of your formula sheet under elementary charge. Is it there? Yeah. Okay, so that's what you use for a proton or electron. Proton just adds a negative to it. Okay. So if we've got two charges, If we got two charges, we find that as you move, let's say this charge is stationary. This is stationary here at this point here. This is your distance r between them. I'll use a different color. It's not as clear as I'd like. Okay. As you go from this to this, so let's say I increase it, I increase the distance. So this is my R initial here. This is final here. Okay, so I moved Q2 out further. We find that the force decreases. I'll just draw it in here. I draw it as a smaller force. It decreases. The farther out you go. Okay, on a graph, we could actually plot it. We could plot it. Yeah? If the distance increases, the force decreases. If you get farther apart, the force decreases. Weaker and weaker and weaker. The farther apart you get, the weaker and weaker it gets.
In this case, the force F1 will be more.
F1 and F2, as we, in this case here, you want to label this. I didn't want to get too worked up with, this is the final case here. This is the initial case here. So you want to be more precise. That's final, that's final. Okay, I didn't want to put too many subscripts, but. I just put it, whatever. Okay. Okay, I'm going to plot this so you can get an idea visually what it means. So this is your force. Okay, it's an electric force. Right? All of those, what I was referring to, are electric forces. I can't put too many subscripts, but it is electric in all cases. So what I just said here, you can express visually in a graph. Oops, I can't draw like this. Okay, that's what you'd get. As you increase your R, your force decreases. And until you get to at R infinity, force is 0. You never get there, but as you get farther and farther out, you get closer and closer to a force of 0. Okay. This is very similar to gravity. Gravity would have the same graph. You can replace the E with G. You get the same looking graph for gravity. Okay, So let's say you doubled the charge. So I'm going to look at this charge here. Okay. Let's say you doubled it. This is your original Q2, except it doubled. Double it, your forces would increase. I'll redraw these. Your force actually, you go back to this diagram here. This is your original force. Your force would double. Double in size. So you double the charge. You double the charge, force doubles. Triple it, force triples. How do you express that mathematically? This is identical to the case of masses. You double the mass, the force doubles. And we're talking about gravity. So the equation should look very similar. The equation is this. This is the equation that tells you how to find the force given the charge. This is a different constant. I'll explain it in a second here. This equation looks very similar to the formula for gravity, except we're not dealing with masses. These are charges. K is a different constant. It's called Coulomb's constant. Okay, and it's got a value of 9 times 10 to the 9. Newtons has to be in newtons because it's going to give you a force. On top, meters squared, because you've got meters squared in the denominator here, divided by what's on top, coulombs squared. Q1 or Q2, it doesn't matter, is the charge in coulombs okay. Obviously, you've got two charges. You got a Q1. You got a first and a second charge in your equation. You need both charges to calculate the force. R is the distance between charges in meters, same as a planet, center to center, same thing with the charge. The charges are so small, they're called point charges. The center is practically, wherever I draw the charge, that is the center of the charge. Charges are really, really small. So distance between charges in meters. Coulombs. I'll put that in green. You're going to get mixed up with the, this is in coulombs. This is in meters. Okay, so this should have been all in green. That's your unit. Very similar to Newton's law for gravity, except it's a different constant. Look at the size of this exponent. It's 10 to the 9 compared to Newton, which is 10 to the minus 11. It's for comparable sized objects, the electric force is a lot bigger. And it's because of this this constant is a lot bigger than the gravitational constant. You don't need much charge to feel an electric force. The reason why you don't feel any gravitational force between you and the person sitting next to you is because you need huge amounts of mass to experience that force. Don't say anything. Don't say anything insulting. But you do need huge amounts of mass to feel gravity. Not so with charge. You don't need much. Okay, so I'll give you some examples using Coulomb's force. You do need to take into account direction. When you've got a case of 3 or more charges, then you need to take into account direction. We'll get into that. So let's write down the following example. Calculate the electric force between charges of 1/1,000,000th of a Coulomb and 1.5 millionth of a Coulomb. Should be and when those two charges are really close together, when they are 5 times 10 to the negative 1 meters. So 50 centimeters apart. Okay, so just before we begin here, sometimes you'll see this. Instead of what I wrote down, you'll see 1 micro Coulomb. This is the same thing as what I wrote down above. This implies it's a symbol. It's called, referred to, it's a Greek symbol or letter. It's called micro. It refers to 1/1,000,000th, 10 to the minus 6. You'll see this as well. You ever heard of nanoparticles? A nano is, obviously a nanoparticle is a very small particle. Nano in meters is 1/1,000,000th. 10 to the minus 9 is 1/1,000,000th. 10 to the 9 zeros is $1 billion. Yes.
Is it the same symbol as the coefficient of friction? Or is that...
It's confusing, but yes. You have to know the context. In this context, you'll see it in front of the coulombs. In that context, it means 10 to the minus 6. Okay, so 1, you'll see this as well sometimes. That means 1 times 10 to the negative 9. 1/1,000,000th of a Coulomb. Mm-hmm.
So that describes like nano, like between nanometer and nanometer.
Yeah, I doubt you'll get. Yeah, usually we use it in the context of coulombs, sometimes meters. Yeah, micrometer, nanometer. Yeah, when you're dealing with microscopic particles. Yes. Okay, so let's do the calculation. I do, just so you know, you'll see me write down this. It's the same equation instead of Q1, Q2. I do that. There's a reason for it. It's coming up later. So it's the same equation. Usually, you don't have to. In this case, it doesn't matter which one you plug in for a big Q. But later on, it's important. Big Q will be the Big Q will be the central charge, usually the bigger charge. Oops. Okay, I'm just going to write down, I don't usually write down the units, but I'll do it this time just so you can see what happens. Units are in green. So we have two charges. We have 1/1,000,000th and 1.5. So it doesn't matter the order. It's just, I better put units. Okay, they are 5 times 10 to the minus 1 apart. Don't forget to square it. This is important you understand. Some equations are squared. Later on, we'll deal with one that's similar to potential energy for gravity that is just simply 1 over r. Okay, and you got to square this. Okay, so I put the units in just so you can see. You end up with what you expect. Units of newtons. Okay, one sec. Coulomb cancels out here. This should be Coulomb squared, by the way. Forgot to write it in. This should be Coulomb squared. Coulomb squared here will cancel out the coulombs on top. Meters here is squared. That's going to cancel out with the meters squared there, leaving you with what you expect. Units of newtons. Yes. I said later on it's going to make more sense. You can write it as Q1, Q2. I like doing it this way because later on we're going to deal with other equations that cancel out the little q. That's why I did it that way. But it doesn't make a difference at this point. Later on it will.
And also,
Yeah.
our final answer for force will be other than coulombs or is it even?
Our answer, if it's a force we're charging or can't, if it's a force that we're trying to calculate, it's in newtons. That's what we're calculating here, force, so it's in newtons. The charge will always be in coulombs. Okay, another example, example 2. Okay. Well, 2-point charges. Of 1.8 of 10 to the minus 6 coulombs and 2.4. Produce a force very weak force, but stronger than gravity. How far apart are the two charges? How far apart? How far apart? This is messy here, but this says point. So 2-point charges of 1.8 million coulombs and 2.4 times 2.4 millionth of a coulomb produce a force 2.2 times 10 to the minus 3. How far apart are the charges? I'm going to use this. You can use Q1, Q2 if you want. I'll do that. Write it as KQQ. Okay, big Q, small q. I would just cross multiply. Cross multiply the distance with the force. And then divide out the force on both sides. So you got R squared. Yeah, be lazy. That's so. Okay. Done. Then take the square root. Yeah, 4.2 meters. This is harder. This next one is harder. Important you draw the diagram for this. So this is a charge. A 1.7 times 10 to the minus 6 is placed two times 10 to the minus 2 from a charge of 2.5 microcoulombs. And calculate the net electric force. I'll draw it. Okay, so I'll draw the distances in here. This is your first charge. And this is your charge that's being acted on. I'll go through all of this again. And this is your third charge. Okay, so let's reread it. It says the charge of this is placed 2 times 10 to the minus 2 meters from a 2.5 microcoulomb charge. So it's this charge here that's being acted on. That's in the middle. And it's 3.5 times 10 to the minus 2 meters from a negative charge. So charge B is what's being acted on. That's in the middle. We're going to find the net force on that. That's it. Okay. So let's just be clear. This is positive. That's positive. That's negative. Let's just redraw this. I'm going to just copy it. Okay. I'm going to erase. You're going to have to redraw it, but I just want to show the forces. You have the force on B that's the force on B due to C. So what's important is whatever comes first, that's what's, in this case, in the middle. That's what's being acted on. Whatever comes after in the subscript is, this should be A, not C. It's true. That's what direction of, just, sorry, I was looking at. This should be A. Whatever comes after the B is what's doing the acting. A is pushing B. The A comes last. Whatever is being pushed comes first. So B comes first. It's being pushed by what? A. And that's the first force. The second force acting on B is due to C. I don't know how big it is, so I'll just draw this arrow a little bit bigger. That's the force on B due to C. It's an attractive force. C is pulling B towards it. So FBA and FBC are both to the right. So we haven't calculated it yet, but the net force on B is equal to FBA, positive value of FBA, the absolute value of FBA plus the absolute value of FBC. Just add them together. That will give you F net. And yes, F net is to the right. That's your F net. Draw it from the tail of the first to the tip of the last. That's your F net. to the right. You're going to have to draw these diagrams with arrows to know where the direction of the net force is. Okay. Yes, you have a question. Yeah, that's why notice I put at the beginning of this, I put the signs of the charges. That's how you tell the direction of the forces. You have to, first of all, be clear on what is being pushed or pulled. It's B. We're not interested in A or C. We're interested in how B is being affected. It says so in the problem. So the first question, you deal with A first and then with C. You deal with one charge at a time. Whatever the charge is on the left, deal with that first and ask yourself the question, is it attracting? Is it pulling B or is it pushing B? It's pushing B to the right. And then forget about A. Now turn your attention to C. Ask the same question. Is C pushing B or is it pulling B? It's pulling B, so it also is to the right. If this was positive, then you'd reverse the direction of this arrow here, be to the left, and you'd end up subtracting. We'll deal with that later. Okay, so to calculate F net, we need FB and FBC. So we have to calculate both of those. So let's do that. So before we write any numbers in, this subscript here and this subscript here have to be on the right side as well. Those are your charges. B and A. Whatever the subscript on the left is the same on the right. Okay. If you go back here, this would be, this is R here. You could call it RBA if you want. This here is RBC squared. Now you can just plug in values. So B is, what do we say? It's 1.7, right? Doesn't matter the order. It's like 2 times 1 is the same thing as 1 times 2. And A, what do we say? It was 2.5. And the distance, what do we say? Is 2 times 10 to the minus 2. Squared. So this works out to be about 96 newtons. Next one, FBC. Okay, we need both FBA, which we just calculated, and FBC. Subscripts are the same on the right as they are on the left for the charges. Doesn't matter the order. Just make sure you use the right charges when doing the calculation. And I'll use RBC for the distance. And then C is 2 times 10 to the minus 6. I'm going to use the absolute value. Don't worry about the sign when you're doing the calculation of force. We're just interested in the absolute value. Square it. So this works out to be, I think it's 25. Just check that. Okay. So what's your F net? Your F net is just here, what I wrote here. FBA plus FBC. Absolute values. 110, 120, 121. Okay. Let's change it. We're going to change it slightly. Similar problem, just slight variation. Everyone got that? Mm-hmm. The whole thing? Mm-hmm.
So the difference between capital Q and lowercase q. Capital Q doesn't have to have higher max than lowercase q, correct?
Later on it will, yeah. I'm just introducing it so you get used to it. Later on, we're going to cancel out the small q. It will be a lesser charge. Yeah. Okay. I'm just going to change one thing in this problem. It's like a part 2 of this problem. Mm-hmm. Yeah, do I have the breakdown? That I don't have here. I could run up to the car and quickly do one. Yeah, I've got a little time to do that at the end. Just give me some time to get through this. I want to give you a good 20 minutes, so that should give me enough time.
You can go down.
Okay. Now this is a part B. And all I'm going to do is change one thing in the diagram. You're welcome. One thing in the diagram. Let me just circle this. Let me change. Whoa. I'm just changing one thing here. Change this to a positive. Everything else remains the same, but this becomes a positive. Same value, except it's positive. Try it out. Don't tell me, try it out. I'll do it for you in a second, but see what you get. What's the force? You're trying to find the net force on B. Okay. So the question is, what changes? Let's just draw this FBA a little bit longer. Here's your FBA. That's still in the same direction. A is going to push B because they're both positive. A is going to push B to the right. What about C? Now C is positive. C is also going to push B. So C is going to push this way. Now, the question is, how do I draw this? Don't answer it, but I'll answer it for you. Do I draw, this is FBC here. It's going to be this way. Now, should I extend that? Is that long enough? Is it going to be shorter than FB, or it's going to be greater than FBA? How do I know? Well, go back to here. What's the actual value of FBC compared to FBA? FBC is 25 compared to FBA, which is 96. FBC doesn't change its magnitude. It's the same size charge that's doing the acting. So the force is smaller. FBC is smaller, and so I was correct in drawing FBC as a smaller arrow. Let's just redraw it here. A little bit bigger. This is FBA. This is FBC. In the opposite direction now. It's in the opposite direction. So F net on B is going to be equal to FBA minus FBC. You're going to subtract FBC because it's acting in the opposite direction. To give you what? To give you the net force. That's the only difference. So it's 96 minus 25. As long as you show me the direction in the diagram, that's good enough. You can add this if you want. To the right. Yeah. Sure. Okay. I've got problems for you to do. You can try these. I'll give them to you. I'll hand them out. Page 270. You're going to do page 270 and 271. One to 8. Scroll down again. Like that?
Yes.
Man, I wish I had a different time. Oops. Okay, so on the handout that I just gave you, start 270, 271. 1 to 8. Everyone got this? Welcome. Interesting. I like that yellow. Okay, guys, I'll try to give you somewhat of a breakdown of the circular motion test. Give me some time. I got to go out to the car.
So we work on the lab right now? Or?
You want to clean up the lab?
No, like.
Grab it. Go ahead.
Oh, wait, so Mr. Kelly, so.
Stop it. Yeah.
So, Mr. Kelly, so here's the thing. This is the formula that I used, which is this much equals V, and this requires the usage of T, right?
Right.
Period.
T is 1 over F, right?
Right. So I can't directly use like this. I have to use 1 divided by this.
Yeah.
Okay.
Yeah.
Okay. Thank you.
You're welcome. I'm gonna. If you want to fix up your lab, if you've got anything you want to, you can grab as long as you submit it back. I'll be right back. Give you a breakdown of the test.
Michael, I'm right.
Yeah, well, you were half right. You're only half right.
I'm completely right. You just divide the 60 by 33.3 and then you get the proper answer.
Yeah, I know.
Oh, that's drastically different. Okay, it's fine.
You can just do this, but then you divide it.
Oh.
Yeah. 0.52. It's like my old answer.
Those radius?
What?
Those radius?
In diameter 30, so radius 15.
415.
Oh, 415, yeah.
Wait a second.
Do that manually and then divide it. Do that manually, find the answer, and then divide that.
Who are you?
Divided, 1 divided by 9. That's just 1.8. Or you can just straight up 60 divided by 30. Should be a small one just past field. Yeah.
Another one after that.
Oh, just sign the whole one.
No, we have, it's electrostatics and I have to make it two.
No, it's a thing. Because, like, we haven't tested it. I would like to go Tuesday. Yeah, and then we'll have the test in the finals on Friday. So what should, what final exam is? Finals? Next week. No, what will it include? What? What units will it include? Everything.
Except for.
But how are we gonna do? Probably just next.
Like, it'll probably take 2 days to cover this one, and then 2 more days to collect it. And then they'll just slap them.
I don't know. I don't know. Yes.
Like, you just put them together into one test, same with like certain movie interpretation. Because they're kind of. What do you get?
So you were saying?
Yeah. Because they're like, yeah.
Wait, right, and then if I go, so this one is right? Oh, this. Okay, this should be right, and then just this, right, so I fix that, and then read. Okay, now I wanna fix up the lab a bit, because I'm not quite sure if my, slope is correct. Total T divided by 2L equals half. It's like this times, this equals 2 times L.
You just try with, I think, this.
Yeah.
Okay, so.
Yeah, you divide the time by the 60 divided by.
Like, I'm trying to find the red. So
T would be
0.2x and
instead of.
oh, okay, yeah.
I think you have like 0.5.
Yeah, they're like your chance.
Same thing.
And then this one is
Yeah, because this is dynamic.
Oh.
I just misread the whole.
That's okay. And then how do you get for T? How do you get 0.77?
It's the same.
That's how y2 minus y1 and y2.
Let's try this one. Mine.
Yeah, how do you get
Alright, so it's 1.57.
This one minus this and this one.
Yeah.
And like if you think of a lot of
Try that. We'll make
interpretations,
the center
and then
line.
we divided the time.
Oh yeah, for
Right?
Yeah.
So then it's 32 rotations per minute, then you're gonna divide the time, so 60 by 33.
that makes so much sense. Thank you.
What are you guys talking about?
Never mind.
Oh, yeah. I still don't have a.
I have to change something.
If I.
Like I just sell it. That's fit line and then.
You said you learned too much about the salt just because we don't actually know how to
No,
do
that's
it.
not part of the thing. Good, good enough.
Okay,
What? And yours in?
I'll finish that, and then I'll do all of this. I'll do all of this.
Wait, I just realized you.
What?
Oh, that's hard.
And now you want to do what? Back in his car. Okay, well, I'll get this done. So please don't laugh out. Actually, no, when he gets back, I was gonna ask her to start.
I actually.
Oh, just for, what would I?
I got divided by one. So this one.
This one is.
One point two seven, does that line up 1.37? Rise over run, right?
Square rooted.
So 1.27 rise over one run.
Okay.
Okay,
That's why.
I'll say I ate smokes. Yeah.
Yeah,
I mean,
yeah. Good, you love this.
Yeah.
You get to write into that. And then they're all into.
I'll understand.
So that's
Oh,
also
right
why
here,
you're
just-
Like, I was like, I don't
Yeah,
find it.
Oh, yeah. You.
Our elevator.
Yeah.
Because then it's still R. Oh, this is new.
Why do some more?
There's not more of a Jonathan, a Pete here.
You still get the same, it's just like your questions.
Okay.
I don't think so.
What?
Yeah, you still get the same thing. For C. For C would be.
So it's just. Yeah.
Yeah.
And you're actually.
This is one.
Yeah, okay, so. Yeah. Okay.
What the frick? No, I don't. I got the right answer.
Yeah.
So again, the slope thing, you're not like really gonna like be too strict on that, right?
Yeah, you do need to know how to calculate a slope, right? So,
Okay, so this is what I did.
Thank you. Oh, sorry.
So what I did was basically this. So for instance, I'm comparing the period to the power of 2 to L. I got the totality of period of to the power of 2 divided by the period of L, because like, so basically there's this equation which has this in here, which is basically the slope.
you added up all the values and then
Yeah.
divided by
Oh, because I divide by that and then 2
No, 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 no,
Is
no,
that
no, no,
supposed
no,
to
no,
get like
no.
an
You gotta
arrow?
know that. You gotta find the difference in choose 2 points. Like I said,
Okay.
that's the way to do it.
So should I just like quickly change it right now?
Yeah, you got time. I'm gonna be doing some. I'm just gonna finish just a breakdown of the test on Wednesday for you now, and then record some stuff and get it back to you.
Well, theoretical slope we have the same one. I'll just quickly do that. Basically what it is
Okay, for the test. All right. For the test on Wednesday. Remember, that includes gravity, right? Circular motion includes orbiting bodies. Got about 10 multiple choice. I'm just giving you some examples of what to go over. I would know moving over the top of a hill. Cover that problem. Cars moving around a corner. Remember with friction. I would know field strength. This is just some possible questions. Gravitational, I'll make sure I'm clear on that. Know how to calculate the gravitational field strength. Okay, make sure you go over that second handout that I gave. You've got the answer to that at the back. I would go over, now there's some questions on that I'll have to eliminate. I'll get to that later though. There are 3 written, and they focus mainly they are satellite type problems. Satellite. Okay, so know how this relates. In the case of period or speed, so you've got two possible, you need to be able to rearrange for whatever you need the following equations. So either this one or this one. Wait, before you copy this second one. You have to be able to use either one, right? Well, that's a G. Bad G. Rearrange to solve for whatever is being asked for. Know the relationship between these two. How does speed change with mass? How does the period change with mass? How does the speed change with radius? How does this period change with radius or distance? I would also know, yeah, there's going to be at least one problem on either the work, either going to be a problem involving an object, a satellite that's lifted. So this is a satellite that's lifted. You need to calculate the work in order to do that, or it'll be involving a falling satellite. Whoa. In which case you have to use this equation. So this is for a falling satellite, falling object. Usually it's calculate speed before it hits. Okay, so that's the basic rundown. I've got to give you a breakdown as far as that second handout, what to go over. I had it. I had a printout for you. I'll go get it. My fault. Just keep working on the lab or keep working on 1 to 8. Everyone done this? I'm going to close it. Stop the recording. Yep, I just got to stop the